Imagine you're sitting in this highly secure, softly lit control room.
Right.
You're staring at these screens, tracking data blocks that are moving at hundreds of miles an hour. And suddenly, over the radio, this voice cuts through all the static and says, ACC reports AAL deviation near controlled airspace.
Which, I mean, sounds like complete alphabet soup to most people.
Exactly. But let that sink in for a second. ACC reports AAL deviation near controlled airspace. If you are sitting in that chair and you don't instinctively process the cascading implications of every single syllable in that sentence, you are already dangerously behind the aircraft.
Oh, yeah. And in this context, being behind isn't just, an inconvenience. It is literally the precursor to a catastrophe.
Yeah, it's the fine line between a routine Tuesday and an international headline. So, welcome to the deep dive. Today, we are extracting the core insights from a massive stack of highly technical, official aviation training documents.
And we're talking comprehensive operational glossaries, rigorous manuals on standardized global aviation phraseology, all of it.
Right. But we aren't doing this just to, memorize definitions. Our mission here is to decode the operational philosophy behind this highly engineered language.
To understand the exact system of communication that keeps millions of people, including you, the listener, safe every single day.
Because these terms, they are way more than just convenient shorthand, right? They represent this global fail-safe architecture.
Yeah, I mean, people tend to think of acronyms in professional settings as a way to save time. Sort of like corporate jargon, like circling back or whatever.
Right, yeah.
But in aviation, while the communication definitely must be fast, speed is entirely secondary to absolute clarity. This language has been engineered over decades and unfortunately usually paid for in blood to basically eliminate ambiguity from human interaction.
Okay, so let's unpack this. Because before we even look at the operational implications of these specific abbreviations, we actually have to examine the auditory architecture of how they're spoken.
Yeah, the phonetics.
Exactly. The source manuals dictate that in aviation, a mispronounced syllable isn't just a grammatical error. It's a literal safety hazard that introduces cognitive lag.
It really is a fundamental layer of operational safety. The source material we have here dedicates massive sections, pages and pages, just to the rigid, globally mandated rules around standard pronunciation.
And this is where it gets highly engineered. Look at the specific examples in the text. Take the major regulatory bodies. The International Civil Aviation Organization is abbreviated ICAO.
Right.
But you never say the individual letters. The manual explicitly mandates the pronunciation ICAO. But on the flip side, if you are referring to the Federal Aviation Administration in the U.S., you absolutely cannot try to pronounce FAA as a word.
No, definitely not.
You must articulate it as FAA.
And that logic extends globally, too. Like the European Union Aviation Safety Agency, that one is pronounced as the word EEASA.
Oh, really?
Yeah, but then the Joint Aviation Authorities requires the distinct spelling JAA.
See, to an outsider, that might seem totally arbitrary. But looking at the operational terms in the glossary, a pattern really emerges, like a weather report, METAR, is spoken as NEH TAR.
Right.
A notice to airmen is NOH TAM. The traffic collision avoidance system is TE CAUS. But then, when an aircraft shifts into visual flight rules, the pilot must state VFR.
Yeah, they cannot slur it into a word. It has to be distinct.
Exactly. Air traffic control is strictly ATC. To me, this reads less like a workplace glossary and more like learning a really highly specific musical tempo.
Oh, that's a good way to put it.
Right. You have this global orchestra, and every single musician, whether they are operating out of Tokyo, London, or Sao Paulo, they must hit the exact same phonetic note regardless of their native language.
What's really fascinating here is the why behind all that phonetic rigidity. The musical tempo analogy is a great framing. We kind of have to add the element of extreme psychological stress to it.
Oh, absolutely.
Because this isn't just regulatory pedantry. These rules exist because a pilot from one side of the world who is maybe speaking English as a second or third language, and an air traffic controller from the other side, also speaking English as a non-native language, they have to transmit and process critical data through a noisy, crackling radio headset in fractions of a second.
So they're basically eliminating the cognitive load of translation.
Entirely, yeah. If a controller says EASA and a pilot's brain is expecting EASIA, That cognitive dissonance, I mean, that half second it takes the prefrontal cortex to process the discrepancy, is literally processing power taken away from flying the aircraft.
Wow.
So the strict phonetics act as this auditory firewall against ambiguity.
And the manuals even apply this to when a term is first introduced into the airspace. Like the abbreviation FL is foundational for altitude, right?
Yes, very common.
But the documents are incredibly explicit. On the very first mention in a radio exchange, you must speak it in full as flight level. Only after that context is securely established can you revert to FL.
Because establishing that baseline is critical. And you see this most acutely during the absolute highest task load phase of flight, which is the takeoff roll.
Right, the velocity milestones.
Exactly. They have mandated verbalizations.
Hmm.
So V1 is spoken V1, VR is VR, V2 is V2.
But those aren't just speeds, are they? Those are physics-based gates.
Yes.
I mean, V1 is the commit to fly speed. Uttering that specific phonetic string means the aircraft is going into the air, even if, God forbid, an engine explodes a second later.
Which is exactly why the pronunciation cannot vary by even a fraction of an inflection. I mean, the co-pilot calling out V1 is acting as a human sensor, triggering a completely non-reversible decision matrix in the captain's brain.
Okay, so the spoken word itself is a structural safety mechanism.
Exactly.
But, verbal precision really only gets you so far if the physical systems don't match the mental model in the cockpit.
Very true.
Which brings us from the vocal communication over to the physical environment. How this highly specific language maps to the ground infrastructure itself.
Right. And the foundational element in the manuals for this mapping is a C. It's just a capital A, a slash, and a lowercase c. And it simply represents aircraft.
And since a lot of you listening are probably familiar with the industry, you know A's is ubiquitous. But what really struck me in the manuals is how this legacy abbreviation persists deep inside modern digital flight management systems.
Oh yeah, it's everywhere.
It's not just a written shorthand anymore on a piece of paper. It's a core data structure.
It acts as the central node. I mean, every piece of data, every altitude restriction, every weather update, it all revolves around the AirGi. But for that act to interface with the physical world, especially when you're approaching an airport under challenging conditions, it relies on legacy visual and radio aids, which introduces the ABN.
Right, the aerodrome beacon. The manuals describe it as the primary visual navigation aid. It's basically the rotating light signal guiding the aircraft to the physical field, cutting through all the visual noise of ground lights at night.
Yeah, and alongside that visual aid, the documents detail the ADF, the automatic direction finder, which is what points the aircraft toward a ground-based radio beacon.
Okay, wait. I have to push back on this reliance on legacy infrastructure for a second.
Okay, go for it.
We are operating in an era of satellite-based augmentation systems, right? We have synthetic vision, ADS-B, we have glass cockpits that can render a full 3D topographical map of the runway in zero visibility weather.
Yeah, it's incredible technology.
So why on earth are official training documents still dedicating significant real estate to pilots looking out the window for a flashing physical light, the ABN, or tuning into an automatic direction finder that is rooted in, 1930s radio technology? The text acknowledges the advanced system, sure, but it explicitly maintains the ADF as an operational necessity. Why?
Well, if we connect this to the bigger picture,
Yeah.
it reveals the aviation industry's deep institutional paranoia regarding single points of failure. You are absolutely right about the precision of GPS and synthetic vision. It's amazing. But a glass cockpit relies on electrical buses, it relies on software architecture, and highly vulnerable satellite signals. GPS jamming and spoofing, they are increasingly common operational hazards today.
So the advanced tech is brittle.
It can be, yeah. The philosophy of aviation is overlapping domains of redundancy. If a solar flare or a targeted jamming event knocks out the digital navigation, the whole satellite architecture fails. So what remains? The physical properties of the universe. The automatic direction finder relies on basic low-frequency radio waves. They are remarkably difficult to disrupt entirely. And the aerodrome beacon is a literal physical photon hitting the pilot's retina.
Wow. So it's an analog insurance policy against a digital collapse.
That is the essence of their fail-safe culture. You never, ever allow a single technical failure to become an unrecoverable event. The ABN and the ADF provide independent vectors of truth.
I love that phrase. Independent vectors of truth.
Right. Because if the screen says the runway is straight ahead, but the ADF needle is pointing left and the ABN is flashing to the left out the window, the pilot immediately knows the digital system is lying to them.
See, here's where it gets really interesting for me. Because once that act confirms its position via the ABN and actually transitions into the airspace, It has to measure its vertical reality.
Oh, yeah. Altitude.
Exactly. And the manuals spend a lot of time reinforcing that altitude is a highly contextual and sometimes extremely dangerous concept if misunderstood.
It is arguably the most critical geometric and thermodynamic puzzle a flight crew manages. The baseline distinction the training material makes here is AAL.
Above aerodrome level, meaning the strict vertical height of the aircraft relative to the specific airport's runway elevation, independent of sea level.
Right.
I like to think of AAL like measuring a skyscraper from the street level.
Yeah.
If you are on the 10th floor, you are 10 floors up relative to the front door.
Yeah, exactly.
It doesn't matter if that skyscraper is built down in a valley in Death Valley or perched up on a peak in the Rockies. Your local geometry is exactly 10 floors up.
That analogy holds up really well for the geometric reality of it. AAL tells the crew the exact physical space remaining between their landing gear and the tarmac. But geometry is only half the equation, and frankly, it's the less lethal half.
Because the air mass itself is dynamic.
Exactly, which introduces ADA.
Aerodrome density altitude. And for anyone listening who understands basic flight dynamics, the implications of ADA are massive. ADA isn't your geometric height at all. It is your altitude corrected for non-standard temperature and pressure.
This is where we transition from simple geometry to thermodynamics. The physical performance of an aircraft is dictated by the density of the air molecules it is moving through. Hot air expands, meaning there are fewer molecules per cubic meter. Low atmospheric pressure does the exact same thing.
Right. So to build on that skyscraper analogy we just used, AAL is knowing you have to climb 10 flights of stairs, but AD dictates the atmosphere inside that stairwell. So climbing those 10 flights on a cool, crisp day, pretty manageable. But if you try to sprint up those exact same 10 flights of stairs while breathing through a cocktail straw in a sauna, oh man, your physical performance completely collapses.
The geometry of the stairs hasn't changed at all, but your kinetic capability has been absolutely decimated. And that is exactly what happens to an aircraft when the aerodrome density altitude is high. The manuals highlight this aggressively because miscalculating ADA fundamentally alters the physics of the takeoff roll.
Because the engines literally have less oxygen to combust, which reduces thrust.
Right.
And the wings have fewer air molecules to deflect downwards, which destroys your lift.
Exactly, the hazard. A pilot might look at their geometric AL and think, oh, I have plenty of runway. But if they are operating out of a high-elevation airport in the middle of summer, say Denver in July, hot and high, the air is dangerously thin, the ADA is incredibly high, so the aircraft is going to consume thousands of extra feet of runway just to achieve the kinetic energy required to break the bond of gravity. If you only respect your AAL and ignore your ADA, you will quite literally run out of concrete before you run out of gravity.
Wow, run out of concrete before you run out of gravity. So ADA is really the physics acting as a reality check on the geometry?
Beautifully put.
And that demands an incredibly high level of situational awareness from the cockpit. But, these aircraft aren't operating in a vacuum. As they manage their ADA and climb through their AAL, transitioning into the en route phase, they enter this massively complex macro system. Someone has to manage the 4D geometry of thousands of aircraft simultaneously.
And that macro management falls entirely to the ACC, the Area Control Center.
Right. The manuals describe the ACC as taking over once the aircraft leaves the terminal airspace. They aren't just, directing traffic around an airport. They are managing the high-speed cruise phase, establishing separation, and optimizing routes across these vast geographical sectors.
They're essentially managing the kinetic energy of the entire airspace. The ACC controllers are the ones who utilize that strict phonetic phraseology we discussed earlier to maintain the structural integrity of these invisible highways in the sky. They are constantly adjusting flight levels and headings to keep metal from touching metal at Mach 0.8.
But aviation is an intersection of human cognition, mechanical engineering, and totally unpredictable weather.
Right.
So the system is incredibly resilient, but the manuals are brutally honest. Failures still occur.
They do.
And that introduces the final and perhaps most vital component of the source material we're looking at today, the AAIB.
The Air Accident Investigation Board. The documents note that when an anomaly or a hull loss occurs, official investigations are spearheaded by bodies like the AAIB in the UK or the NTSB in the United States or the BEA in France.
But it's not just the existence of the AAIB that stands out in the reading. It's their core operational doctrine. The manual emphasizes that their primary directive is to answer one question: what happened and why? The objective is fundamentally structurally designed to avoid assigning blame.
Right.
They are hunting for the root cause strictly to prevent recurrence.
It represents a massive paradigm shift known in the industry as a just culture. Because in most industries, if a catastrophic failure occurs, the immediate corporate impulse is to find the person who made the mistake, terminate them, and declare the problem solved.
Oh, absolutely. Find the scapegoat.
Exactly. But aviation realized decades ago that human error is a symptom, not a cause.
Okay, so what does this all mean for the architecture of the system? Like, if the AAIB launches an investigation into an airspace deviation, does that automatically imply the ACC controllers or the flight crew demonstrated gross negligence?
This raises a really important question about what we call the Swiss cheese model of accident causation.
Yeah.
The existence of an investigation almost never points to a single point of human failure.
Okay.
We have to synthesize all the layers we've decoded today. An accident is an alignment of vulnerabilities.
Like the holes in the Swiss cheese lining up.
Precisely. The AAIB investigates the entire web. They ask, did the cognitive firewall of the phonetic pronunciation fail under extreme stress?
Right.
Did the redundant analog systems, the ABN or the ADF, provide conflicting data to the digital flight management system? Was the thermodynamic reality of the ADA improperly integrated into the crew's mental model of their AIL?
So they deconstruct the entire operational philosophy we just discussed.
They do, and because the culture prioritizes prevention over punishment, pilots and controllers actually proactively report their own mistakes.
Wow, really?
Yeah, they submit reports saying, I miscalculated the ADA today and almost overran the runway because the ATIS weather report was formatted confusingly.
And instead of firing the pilot, the system redesigns how the weather report is formatted globally.
Exactly. That is the profound genius of the system. The AAIB basically acts as the immune system for global aviation. Every failure, every mispronounced syllable, every misunderstood altitude is fed right back into the training manuals we're analyzing today.
That's amazing.
It is an industry that achieves its staggering safety record by systematically monetizing its own failures into standardized knowledge.
It's just an incredible feedback loop. So to recap the insights from this deep dive for you, we started by examining the auditory architecture, right? Understanding how rigid phonetic rules for terms like ICAO and V1 serve as these cognitive firewalls against fatal misunderstandings. Then we explored how legacy ground systems like the ABN and the ADF persist, not out of nostalgia, but as crucial analog fail-safes against a digital collapse. We navigated the lethal difference between the geometry of AAL and the thermodynamic reality of ADA.
And finally, we saw how the ACC manages this complex ballet backed by the AAIB's relentless, totally blame-free pursuit of systemic improvement.
It is a masterclass in treating communication and failure analysis as hard engineering disciplines.
It truly is.
It really is. And as you, the listener, step away from this, consider how applying that AAIB doctrine, a strict prevent, don't blame framework, how that could radically alter your own professional environment.
Yeah, that's a great point.
When a project derails or a system fails in your organization, notice whether the immediate energy goes toward identifying the culprit or auditing the system that allowed a human error to manifest into a failure in the first place. Fostering an environment where mistakes are data points rather than fireable offenses is really the only way to build true operational resilience.
Shifting from a culture of self-preservation to a culture of systemic analysis. It's uncomfortable at first, but it is the prerequisite for high reliability.
Absolutely. And to leave you with a final provocative thought today, I want you to take the concept of ADA, the aerodrome density altitude, and apply it metaphorically to your own life.
Oh, I like this. Translating the thermodynamics into human performance.
Exactly, because we spend so much time evaluating our geometric progress, our AAL. You look at your career, your relationships, or your personal milestones, and you judge yourself purely based on your altitude. You think, I should be higher up by now, I should be climbing faster.
Right.
But how often do you fail to calculate your personal AEA?
We rarely account for the temperature and pressure of the environment we are actually operating within.
Right. If you are enduring a season of grief, navigating a toxic work environment, recovering from burnout, or managing chronic stress, the air around you is thin, the pressure is unpredictable, your personal density altitude is dangerously high. And just like an aircraft taking off in Denver in July, the physics of your performance fundamentally change.
The kinetic energy required just to maintain level flight in those conditions is immense.
So sometimes, if you feel like you are consuming way too much runway just to get out of bed, or your engine isn't generating the thrust it used to, it isn't a failure of your drive or your talent or your geometry. It is the thermodynamic reality of the environment you are currently operating in.
That's powerful.
You must calculate your ADA, not just your AAL. Give yourself the longer runway. Respect the physics of your situation. And just like that highly trained professional in the control room, the next time you hear the language of the sky, you'll understand the massive, invisible architecture of safety silently holding it all together.